Okay. Ladies and gentlemen, let's continue with chapter 11 out of the textbook of Sengel and Gijar. Not chapter 10, chapter 11. Chapter 11 is on heat exchangers. We've already completed the first part, which were on the types of heat exchangers, the overall heat transfer coefficient, the analysis of heat exchangers, and then there are two very important sections in this part of the textbook. The one is the LMTD method, and the other one is the overall, the effectiveness NTU method. Now, with the previous lecture, we've started with the LMTD method. We've done the method, and we've done one example, but that is not enough. There's one more example that I would like to do with you before we're going to proceed with the second method, which is the effectiveness NTU method. And the problem example that I want to do is example 11.3. It is a steam condenser. So it says steam is in the condenser of a power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water from a nearby lake, which enters the tube of the condenser at 14 degrees Celsius and leaves at 22 degrees Celsius. The surface area of the tubes is 45 square meters, and the overall heat transfer coefficient is 2,100 watts per square meter degree Kelvin. Determine the mass flow rate of the cooling water needed and the rate of condensation of the steam in the condenser. Okay, so here's the condenser, steam condensing at 30 degrees Celsius, and then we've got cooling water from a nearby lake which circulates and condenses the steam. And the water enters at 14 degrees Celsius and its exit temperature is 22 degrees Celsius. What is also given is the surface area of the heat transfer of the tubes, which is equal to 45 square meters, and the overall heat transfer coefficient is 2,100 watts per square meter Kelvin. And they ask us to determine the mass flow rate of the steam, which is the hot side, and also the mass flow rate of the cooling water. So the mass flow rate of the two streams. Okay. Now, when you're going to get a problem like this in industry or in the exam, you're going to look at this and you're going to see, well, I've got two temperatures, but I don't have the mass flow rate. So I cannot determine the heat transfer rate. Okay. And then you're going to look at this side and you're going to see, well, 30 degrees Celsius inlet, and now I don't have an outlet temperature. Okay. But that is where you make the mistake. Okay. Because, remember, what happens during condensation, if you look on a TS diagram, condensation, the steam changes from a gas to a liquid, and it happens at a constant temperature. Okay. So if it has been given to you that you've got a boiler or evaporator, a condenser or anything like that, and one temperature is given, then you've got both temperatures. And it's not all. You also, from the steam tables, can get the change in enthalpy. Okay. Okay, so if we now look at the two streams, now that we know what happens with the steam, and we show it on a TX diagram, although the X might not be there, okay, because we are going to force this heat exchanger to be a sort of a counterflow heat exchanger. Okay, so the steam temperature remains constant. The inlet temperature is 30 and the outlet temperature is also 30. And that is TH, that is the hot side. And let's show the direction in that direction, because we can, and we just choose it like that. Okay, now To condense that steam, we've got cool water from a lake which enters this condenser. So it enters at 14 degrees Celsius and it exits at 22 degrees Celsius. Okay, and that is the cooling side. Okay, so the heat transfer rate is obviously going to be from the steam to the water. Okay, that is going to be the direction of heat transfer. And on this side, we actually have, let's call it delta T1, which is this temperature change, which is 8 degrees Celsius. And on this side, we have delta T2, which is equal to 16 degrees Celsius. Okay, so we can actually calculate the LMTD. So the LMTD temperature difference, and we've derived it, how it is being done, is always this temperature difference, which is 8. Okay, 30 minus 22 is 8 degrees Celsius, minus this temperature difference, 30 minus 14, which is 16, divided by the ln of 8 divided by 16, and that gives an effective temperature difference of 11.5 degrees Celsius. Okay. Now we can calculate the heat transfer rate. It's equal to UA multiplied by F LMTD. The overall heat transfer coefficient is given as 2,100. The surface area is given as 45 square meters. Okay. F is equal to 1, the correction factor. Why? Because we've got condensation. Okay. If we've got a heat exchanger which is not a parallel flow or a counter flow, we have to use the tables in terms of the F values and the R values and the P values to determine the correction factor. Okay. Now in that, we've got an R or a P, and the delta T is going to be 0 or infinite in one of those two terms. So we've said in general, the moment we've got boiling or condensation on one of the streams, then F is equal to 1. Okay. Multiplied by the LMTD, which is equal to 11.5, and that gives us a heat transfer rate of 1,087 kilowatts. Okay, 1,087 kilowatts. Right. Now that we know the heat transfer rate, we can calculate the mass flow rates of both streams. Okay, let's look at the hot stream. For the hot stream, the heat transfer rate is equal to the mass flow rate multiplied by Cp multiplied by Th in minus Th out. Okay, you happy with that? Samantha, what's wrong? Yes, because it is in a two-phase flow region, the Cp doesn't exist. So we cannot use that. That is for a single-phase fluid. It is equal to the mass flow rate multiplied by HFG. Okay, the heat transfer rate we have determined as 1,087 kilowatts is equal to the mass flow rate on the hot side multiplied by HFG. And HFG we can get from the steam tables or from your textbook from table A9. From table A9, and from this we can now calculate the mass flow rate on the hot side, which is equal to 0.45 kilograms per second. Okay, now on the cooling side, it is a single phase fluid, it is water, and now we can say it is equal to the mass flow rate multiplied by Cp multiplied by Tc out minus Tc in. The heat transfer rate is equal to 1087 kilowatts. It's equal to the mass flow rate on the cold side multiplied by Cp of water, typically between temperatures of 22 and 14, it would be 4184, multiplied by the outlet temperature, which is 22, minus the inlet temperature, which is 14. So it is very simple to calculate the mass flow rate of the water as 32.5 kilograms per second. Okay, any questions? Nothing? Okay, what this problem also shows us is how much energy is into steam. Okay, just look at this problem. The temperatures of 30 and 14 and 22, both water. Okay, in the one case it is steam. Okay, to do the heat transfer rate of the steam, we only need about 0.45 kilograms per second, but on the water side, 32.5 kilograms per second. For the same heat transfer rate. You see? Okay. Right. Now the next part in the textbook is the effectiveness NTU method. Paragraph 11.5 in the textbook of Sengel and Gejar. Okay. Okay, now this method is specifically very